So the last part of our lesson here on basically concurrent collectors and non-concurrent collectors is a demo. It's always fun to do a demo because we can actually look at the code and see how things work, and you can compare and contrast different approaches and so on. And this is going to demonstrate the changes and the differences between concurrent and non-concurrent collectors for different types of data structures. And this is to be found in my EX14 folder in my GitHub repository. So as I've discussed a number of times, concurrent and non-concurrent collectors perform differently when used for parallel and sequential streams on different sized input. And we've talked about some aspects of this before when we were talking about splitterators. And if you recall, I talked about the fact that things like an array list splitterator works differently in a parallel stream than, say, a linked list splitterator because of the fact that array lists can split evenly and efficiently, whereas linked lists can't. Non-concurrent collectors operate by merging subresults. I think you probably know that by now. And that means that different threads operate on different instances of these intermediate result containers. Conversely, the concurrent collectors, as we've talked about, have a single concurrent mutable result container that accumulates all the elements from multiple threads that are running as part of the apply phase in the split, apply, combine paradigm. So there's only one of them. As a result, there's no need to merge any intermediate subresults. So what we're going to do here is we're going to take a look at what happens to different types of collectors when we run it on input, and the input gets bigger and bigger and bigger. And we're going to use different kinds of mechanisms to be able to merge the results together or not, depending on whether we're doing concurrent or non-concurrent collectors. And so the example here, again, as we saw before, is we're going to use the works of Shakespeare and the words in the works of Shakespeare. And we're going to run basically 4 tests, one looking at the first 1,000 words in Shakespeare, then the next 10,000 words, or the first 10,000 words in Shakespeare, then the first 100,000 words in Shakespeare, and then all the words in Shakespeare. And what you're going to see here is the difference between the concurrent and non-concurrent collectors becomes more pronounced as the size of the input grows. So when we've got basically a small number, just 1,000, the times are close to being the same. But when we get to all the works of Shakespeare, we're going to see that you really start to get a big win with respect to using parallel streams and with respect to using concurrent collectors with parallel streams. And that's the key take-home point for this part of the discussion. So what I'm going to do now is I'm going to switch over to look at the code, and we'll walk through this and we'll get a chance to see a whole bunch of really cool things. So here's the code we're looking at. This is the EX14 example, and we're going to start by looking at the EX14 class, which is where all the heavy lifting gets done. And this basically shows the difference in overhead for using a parallel splitterator for linked list versus array list. We've already done that, so I'm going to skip over that. And then we're going to look at the difference in overhead between combining and collecting results in a parallel stream versus a sequential stream using concurrent and non-concurrent collectors. So here's the program. We're going to run it for a certain number of iterations. We're going to get the works of Shakespeare, and then we're going to warm things up. We've already run the splitterator test, so we're going to uncomment, or we're going to comment that out. And what we're going to do here is we're going to run the collector tests. And what I'm going to do is I'm going to start this running because it takes a little while to run. And while it's running, we will go ahead and keep looking at the code. So if we set that and run it, it'll go off on its merry way. And while that's running, I'm going to go back over here and we'll look at the implementation. And by the time we're done, it should be finished. So we can skip over the splitterator tests. We've already done them. We're going to split over the joining tests because we're not talking about that topic at this point. And what we're going to focus on are the collector tests. And so what we're going to do here is we're going to have different sizes of input, 1,000, 10,000, 100,000, and then up to 1,000,000. There's only 800 some thousand words in Shakespeare, so it won't quite get to 1,000,000, but it's the whole kit and caboodle. And what we're going to do is we're going to, for each of these different sizes, we're going to have the for each method called. So for 1,000, for 10,000, for 100,000, for 1,000,000, and so on. We're going to get all the words in Shakespeare and the complete works of Shakespeare using a regular expression to split them up based on the word separator, which is just white space. And we put a limit which says only take that many. So let's just for kicks, let's go take a look at that method. What this does is it takes the file name, opens it up, reads all the bytes in that file, which is the complete works of Shakespeare. Then it compiles a regular expression using the splitter, which is the white space regular expression. And so now we're going to have a stream of strings that correspond to just the words in Shakespeare. So we split as stream the complete works of Shakespeare. So we get a stream of words. And then we're going to go ahead and filter out any empty strings. And we're only going to take up to the limit number of the elements. So we're going to use this short-circuiting intermediate operation, which of course is stateful. And that will be used to only get the designated number, 1,000, 10,000, 100,000, and so on. And then we collect the results into a list of strings. So that's what we're going to get back. All right, so popping back out of here for a second, we're then going to go ahead and start the tests. And you can see here what we do is for each different size of input, we're going to run 4 tests. We're going to do time, stream, collect to set, and we're either going to use it being done in parallel false or parallel true. So we're going to run it sequentially and in parallel to do the collect to set mechanism. And that's going to use a non-concurrent collector. And then we're also going to run another test called time, stream, collect to concurrent set, which is a concurrent collector. And once again, we're going to either do that in parallel or sequentially. So we start out by doing it sequentially, and then we also do it in parallel. And when we're all done, we're going to print the results that we get. And we'll go and look at those results in a second. They're probably done by now, but I'll let it keep running. Let's go ahead and take a look at these methods. We'll start with time, stream, collect to set. And what this does is this is a method that determines how long it takes to collect partial results into a hash set. So this, of course, is going to be using non-concurrent collectors. So it'll either be using non-concurrent collectors for a parallel stream, or it'll use non-concurrent collectors on a sequential stream. When it starts up, we run the garbage collector to make sure everybody starts with a common complete set of memory. We then update the test name to include whether or not it's parallel or sequential. And then we go ahead and use our little time run, a utility class and utility method in order to time how long it takes to do the following. So we're going to iterate through this from 0 to less than max iterations, which is set to 10, as you can see here. And for the list of words, which will be 1,000, 10,000, 100,000, and so on, we convert those words into a stream. We can conditionally turn the stream into a parallel stream or not. Let's assume it's sequential, then everything's done sequentially. That follows. If it's parallel, everything that follows is done in parallel. And then we go through the stream and we convert all the strings to lowercase. So they're all lowercase just to make them all consistent so we don't end up with lowercase and uppercase words being counted differently. And then we go ahead and collect into a hash set. So this is using the non-concurrent collector, and we're going to collect the results either sequentially or in parallel into a non-concurrent collector. Let's go down here and take a look at the same basic logic, except this time we're going to use a concurrent collector instead of a non-concurrent collector. So the overall structure of the test is almost identical. We garbage collect everything. We set the name to be either parallel or sequential, just for debugging purposes and output purposes. And then we go ahead and run through a number of iterations. We conditionally convert the stream to be parallel or sequential, depending on what we're doing for our test driver. And then down here, we have the same logic. We take everything in the stream, convert all the words to lowercase, except this time we're going to use a concurrent collector, which in this case is concurrent hash set collector, which I'll show you in a second. And so we go ahead and get a concurrent hash set collector, and all of this code is then done in concurrent mode with a concurrent collector. So let's go over, before we look at any more of the code, let's go see if the tests have finished. They have finished. So you can see here that these are sorted by best performance. So the thing that appears first is the best performing. For 1,000 words, it actually turns out that it doesn't really matter if it's sequential or parallel. In fact, in this particular run, sequential is faster than parallel. demonstrating that parallel streams don't always give you an advantage if you have a small number of elements and you're not doing much work on each element. So sequential is winning for a small input size. When we get 10,000 words instead of 1,000 words, now parallel stuff is working best and working best with non-concurrent collectors. So again, for relatively small input, the non-concurrent collector stuff is working fine. Conversely, you can see that the parallel collector is taking the slowest time when you have a relatively small input because there's overhead for setting up parallelism. When we get to the 100,000 word level, you can see that we're still, that parallel is working best for non-concurrent collectors. So we haven't reached the point yet where we're getting a win for doing concurrent collectors. So, but parallel still is running the best, but the parallel concurrent collector is running the worst. But finally, when we get to all the words in Shakespeare, we finally get a win from parallelism. So you can see here that the concurrent collector now performs the best when run in parallel. So we get the best performance with the parallel implementation, and the second best is for the non-concurrent parallel version, but notice it's like twice as slow, and then the sequential versions are substantially slower, right? So the basic bottom line here is that is almost always the case, parallel computing works most effectively, and parallel streams work most effectively when n gets big, the number of elements, and when there's a lot of processing taking place. And so you start to slowly see this phase transition where the overhead of merging gets higher than the overhead of synchronization. And so this is exactly what we would expect. Obviously, your mileage may vary a little bit depending on your hardware. This is running on an 8-core hyper-threaded processor set, so it's got a lot of parallelism that's potentially there. But once again, you don't really get the bang for your buck until you have a large number of elements to deal with. Let's go ahead and pop back to the actual source code, though, because there are a few more things I want to show you now that you've seen the results. So let's go ahead and take a look at the concurrent hash set collector. And let's see if I can make that come up. So here's concurrent hash set collector. This is the collector that we implemented to implement concurrent semantics for a hash set. I'll also, of course, have to explain to you what a hash set is, or concurrent hash set. So here's the concurrent hash set collector. You can see it implements collector, and it takes elements of type T, which is the parameter to the concurrent hash set collector class. And then it has an accumulator that's a concurrent hash set, which we'll look at in a second. And then the return type is also concurrent hash set. So that gives you an indication we probably don't need to have a finisher here. Here is the supplier method, which just returns a new concurrent hash set. So it's a constructor reference that makes a concurrent hash set. We'll look at that in a second. Here is the accumulator, which, as you can see, returns the add method on concurrent hash set. Here's the combiner, because this is a concurrent collector. The combiner is a no-op. Here's the finisher. This can also be a no-op because we're going to set the identity finish characteristic. And then finally, here's the characteristics metadata method, the factory method that returns the metadata for this particular kind of collector. And you can see it's concurrent, unordered, and identity finish, all the things that we want to have set. Oh, and then there's one more factory method that just makes a new instance of concurrent hash set collector. I call it toSet. Concurrent hash set is a simple wrapper around concurrent hash map. So you can see that concurrent hash set extends abstract set and implements set, so it gets the right characteristics we need to be basically a concurrent hash set or a hash set. We have a field that's the concurrent map. That's what we're going to use as our implementation. We have a dummy value that we're going to use here to store as the value, because we're going to basically have a concurrent hash map where we only use its keys, and we always use the dummy value for the value because we don't need a value. We go ahead and make ourselves an instance of concurrent hash map and store it into the mmap field. And then basically all the methods in here are just going to forward to the underlying field that holds the instance of concurrent hash map. And you can see here when the add method is called, for example, it puts the element, which is the one and only element, into the map as the key, and it puts this dummy value as the value because we don't care about the value. So this is just a little wrapper that means we don't have to re-implement all this stuff because concurrent hash map does a really good job of being efficient, and there's no need for us to reinvent the wheel here. So there's just a bunch of little helper methods that do all the forwarding and the various things that we need in order to make this work properly. So that's concurrent hash set, just a simple wrapper. So this is basically the end of the discussion about the implementation of the EX14 code. And hopefully you now have a better idea of how to implement a concurrent hash map, or concurrent hash set, a concurrent hash set collector, and then you also know better about what the performance implications are of using one versus the other. So that wraps up our demonstration showing the differences between concurrent and non-concurrent collectors. And that way, I think you'll have a good idea of how this stuff can actually be used in practice.